Next is Thomas Rimlinger. I'm doing on the origin and evolution of the Kepler-36 system.
All right, hello. So as Thomas said, my name is Thomas Rimlinger, and we're going to be talking about Kepler-36 today. So for those of you unfamiliar with this system, Kepler-36 is a sunlike star which has two exoplanets orbiting it, and they were discovered in 2012. And so some interesting facts about them are listed here. And the main thing that jumps out at you is density contrast. So the inner planet, designated B, is considerably denser than Earth, and is about 8 times denser than the outer planet, Kepler-36c. So we designate B as a super-Earth with a mass of about 4.5 Earth masses, and the outer planet as sub-Neptune at about 8 Earth masses. And the other thing that's really significant here is how tightly packed they are. So their semimajor axes differ by only about 1/100 of an AU. And in fact, these planets occupy a 7-to-6 mean motional resonance. And so these two facts, the density contrast and the 7-to-6 resonance, make this a very unusual system. We don't usually see 7-to-6 resonances among the survey of planets from Kepler and other telescopes. And just standard solar system formation models indicate that high density and low density planets should not be this close to each other. And so we have to ask ourselves, what's going on here? How did these planets get here? What's going on? Okay, so the first people to attack this problem from a dynamic standpoint were Quillen et al. In 2013. And in their paper, they argued that you put these two planets, or protoplanets, in a protoplanetary disk, and they are bombarded with Mars mass embryos, which originate exterior to the planets. And so these Mars mass embryos are migrating in very rapidly and bombarding these planets. And in order to get the density contrast, Quillen et al. Argued that the outer planet would have its mantle stripped. So the lighter material towards the crust of the planet will be stripped away, leaving only the dense material in the core. And that's how you get huge density contrast. And then, in addition to that, you have to have planet switching, so planet position switching. So since the outer planet will be perfectly struck by these embryos, you have to get it inside of the inner planet, which would not be the outer planet, in order to get the more dense planet to be on the inside. So in their paper, they reported on 30 simulations, 2 of which resulted in 7-to-6 capture. And so I've kind of already hinted at the weaknesses that we saw in this paper. So potentially, it is very difficult to get mantle stripping to effectively raise the density of the planet, because a lot of the material that would be stripped off might reaccrete anyway later on. And so that might not necessarily raise the density at all. In fact, it might lower it. And furthermore, when you get this kind of position switching, oftentimes that can leave the system with one planet in a very highly elliptical bound orbit, or even an unbound orbit entirely. So we felt that these were considerable weaknesses, because in order to get their simulations to result in 7-to-6 capture with the appropriate density contrast, Quillen et al. Required considerable fine-tuning. Okay, so our approach is motivated by Quillen et al. With a few differences. So in our approach, we imagine, just as before, we have these two two planets in the protoplanetary disk migrating inwards. Instead, however, of having embryos originating exterior to them and migrating inward very rapidly, we have them originating interior. And so we imagine that the outer planet, which is the more massive planet, will be migrating in more quickly than the inner one because it has more mass. And so very quickly, we would expect that the outer planet would capture the inner planet in a 2-to-1 resonance, and they would just migrate in together. And as this inner planet migrated inwards with the outer planet, sort of in lockstep, it would sort of shovel up material in front of it. And all these accretionary impacts onto the planet would add mass to it, and ultimately, if you added enough mass, the inner planet's own self-gravity could cause it to contract, and therefore get you the density contrast. And so, right. In addition, these accretionary events, these impacts, could potentially knock the inner planet out of the 2-to-1 resonance potentially into a higher one, like the 3-to-2, or the 4-to-3, or eventually the 7-to-6. So that's the basic idea that we have for how this system could have come about. These two planets migrating in and sort of shoveling, and the inner planet sort of shoveling up this material in front of it as it progresses. So let's see, can we get this to work? And the answer is yes, of course, or I probably wouldn't be here in the first place. And so, so this is more of a proof of concept than an absolute way of saying this is definitely how it happened. But in the simulation, it's not difficult to see. But so, so there are six plots here. The top three, 1, 2, 3, are the semimajor axis, eccentricity, and inclination of the inner planet, designated with subscript 1. And the bottom three are semimajor axis, eccentricity, and inclination of the outer planet. And so the initial conditions of the simulation are we start the inner planet at 2 AU, the outer planet at 5 AU. The inner planet starts out with about an Earth mass less of mass than it currently has, and the outer planet starts out with roughly the current amount of mass that we've measured for it. They both start out with very low eccentricities, and there is, for simplicity of the simulation to save on integration time, the inner planet was given no semimajor axis drag. The outer planet was given semimajor axis drag, as you can see. So it's migrating in here, it's getting closer to the star. And in terms of eccentricity damping that you'd expect from the disk, the inner planet has very, very weak eccentricity damping, and the outer planet has stronger eccentricity damping, again, because of its mass. And so, finally, we have 5 collisions in the direction of the inner planet's velocity. And these collisions are modeled as impulses. And so, what do we get? So, after the first collision, which happens right here, although it's somewhat difficult to see, it knocks the planet outward a little bit, but doesn't really do anything. You can see that the inner planet's not moving before the impulse, not moving after the impulse. However, after the second impulse, you can see that it gets caught into the one resonance and then starts migrating inwards. And so at this point, the inner planet is now in 2-to-1 resonance with the outer planet. And at the third impulse, something very interesting happens. So at the third impulse, notice that since this eccentricity has reached a moderately high value of around 0.3 after the second impulse, because the inner planet's eccentricity is so high, when it gets to this third impulse, it can sort of slide through multiple resonances. So instead of getting caught in the 3 to 2, it's actually able to slide through multiple resonances all the way to 5 to 4, where it stabilizes here. And then one final impulse is sufficient to kick it from the 5 to 4 into the 7 to 6, where it stays stable for the rest of the simulation. So it worked. Yay, we can all go home. Of course, this is not an entirely physical simulation, obviously, right? Because we only have 5 impulses, and they all conveniently in the direction of the inner planet's velocity. Furthermore, throughout all our collisions, we've only accreted about 1/5 of an Earth mass. Thank you. And as I said at the beginning, we need to accrete about 5 times, 6 times more than that. So that's kind of where we are right now. We're still investigating what we can do to solve these problems. But so we need to incorporate more randomness in our impacts. So we can't always have 5 impacts. They can't always be in the direction of velocity, etc. But what this means is that since we could potentially have impacts that were not in the direction of velocity, or maybe like opposite direction of velocity, for example, these impacts might not necessarily do anything to the resonance status, but they would serve to sort of accrete mass without actually, doing anything in the system, other than knocking the planet inward, where the outer planet would just come in again and pick it up anyway. So basically, by adding more randomness, we can accrete more mass by having more embryos that do less in terms of the actual dynamics of the system. And so that can help us solve our total mass accretion problem by increasing the amount of mass that we accrete. And so that's all I have. So thank you for your time.
Have you thought about, from your simulations that didn't end up in the 7 to 6, how many planets undergoing this process would have, gone by that and collided or scattered?
Yes, exactly. So the fact that this is such a rare system indicates that this process the process that I showed in the simulation probably doesn't happen that often. And what you're suggesting probably is much more common. And so, in a way, that can be viewed as the strength of the model, that it's so easy to break. Because if it were very, if it were difficult to break this model, then we would see, every system or a lot of systems in the 76 resonance. But the fact that we don't indicates that, in general, something like you suggested would probably happen, and we wouldn't get into the 76 resonance. Yes.
All the way back.
Does this system fit into the scenario of in situ formation?
Well, no. So we don't believe that these planets could have formed where they are. So in the simulation we had, so traditionally we would expect that low density planets like Jupiter, Saturn would form outside of the frost line, right? And so that's what we pictured here. So we imagined that the low density sub-Neptune outer planet would have formed well past the frost line, where the super Earth would have formed inside the frost line, and then they would start migrating in together. So no, we don't believe that this would be in situ coordination.
Is there any indication that any possibility that this could, the forward Earth mass thing could have been a moon that escaped from the sub-Neptune?
That would be a pretty massive moon.
Yeah.
Yes, it's possible. I honestly, I don't know. I can't give you a good answer. I'm sorry.
Yeah, James?
Maybe I missed this, but I'm a little confused how accreting rocks, different amounts of rocks, could explain the density contrast, given we suspect C probably has a higher helium rich envelope and B has no envelope.
Right. So the idea is that by accreting sufficient mass, the planet's own self-gravity will just cause it to crunch down. So the more mass it has, the stronger its self-gravity will be, and thus the more it will try to naturally contract. And so if it sounds like I'm kind of waving my hands, it's because I am. We haven't, most of the simulation has just been working on getting this 76 resonance. So this is more of a proof of concept simulation than anything else. So the basic, so yeah, I can't say much more about the density contrast than I already have. So we would expect that self-gravity in this model would be responsible for density contrast, but I haven't explicitly tested that or gotten the statistics on it.
Anybody else? All right, thanks Thomas again.